So today I'll focus on the first of the two necessary conditions. So what we're going to do is first I have to give you many definitions just so I could even state what this maximal Rado condition is. It's a little bit unfortunate, but that's about 4 or 5 definitions. Then after I state it, I'm going to verify for you guys that the polynomial wx squared minus y minus z satisfies this condition. And hopefully this is not a surprise to any of you. Excuse me. Because we know that for any coloring of the integers, we can get arbitrarily long geometric progressions and their common difference. So we can get wx and wx squared. So that would be what we get if we just had this. And now if you add extra variable, it is still partition regular. Now, I mean, this is not literally a proof of that. It's an intuitive proof, but I guarantee you that this is still partition regular. So it's good to see that it satisfies the condition. We will partially verify that this polynomial does not satisfy the condition. And I will state without proof that this is not partition regular. And then, and then we will show fully that this polynomial w squared x squared minus y minus z does not satisfy the maximal Rado condition and is consequently not partition regular. So this is interesting because Sarkozy gave, in my opinion, quite an involved proof, a fairly non-trivial proof, that the equation x plus y equals z squared is not partition regular. Now, I have tried to work with that proof and generalize it, and you can show, using the same proof as Sarkozy, that this more general equation, k1x plus k2y equals z squared, is not partition regular if k1 and k2 are positive. But his proof does not easily extend to this w squared x squared. Sorry, maybe I could have chosen the variables a little bit more consistently, but you know, if you replace just the square with a product of squares, then his proof does not work. But this maximal Rado condition from Joel and company will show that this is not partition regular. And then if we still have time after we've done this, I'll try to show you the proof. But I figured you might enjoy starting off with something slightly more concrete before we get into this proof. Now, I did essentially take all of the definitions word for word from the paper, and there we go. That's what this is about. So I copied the definitions word for word, and the proof I didn't copy word for word, but I more or less copied it as much as I could. So might as well just remind you that, I don't know, just inform you that this is the case. The examples I did pick slightly differently than what is in their paper. So let's begin with some of our definitions so that we could state what this maximal Rado condition is. So if we have an n variable polynomial, then we let the support of P denote the collection of alpha such that you could write this polynomial as a sum of a constant times a monomial with this exponent alpha. And I don't know, I think examples are more instructive than the abstract definition in this case. So, you know, if we take some polynomials like x squared plus y squared, then the support is 2, 0. right? 2, 0 corresponds to x squared, and 0, 2 corresponds to y squared. So those are the monomials. Similarly, if we take x, y, z plus 1, then 0, 0, 0 corresponds to the constant term. 1, 1, 1 corresponds to the term x, y, z. And if we take yet another example, which is wx plus y plus z squared, then 1, 1, 0, 0 corresponds to wx. 0, 0, 1, 0 corresponds to y. And 0, 0, 0, 2 corresponds to z squared. Any questions about the definition of the support of a polynomial? Hopefully the examples made it clear enough. Now, this definition, unfortunately, I don't know. It doesn't really make sense why it's here or why it's relevant until you see the proof. But I think you can work with it, as I will in the examples. So if we're given a positive linear map from Zn to Z, we could write that concretely as a map that sends integers alpha 1 to alpha n to the integer t1 alpha 1 plus tn alpha n, where these t1 to tn's are going to be non-negative integers. I actually think they're positive in all the examples that I use. I don't really know how important it is to allow them to be 0, but he had that in his paper.
What do you mean by positive map?
I believe positive is just referring to the fact that all of these coefficients are non-negative. And as will be the case in our examples, all of the coefficients will be strictly positive.
Okay, thanks.
Now, if we have a finite coloring C of the natural numbers, then this map is called C monochromatic if the coefficients are monochromatic under the coloring. And then a polynomial, if we're given a polynomial, then we can write the increasing enumeration m0 to ml of the image of the support under this positive linear map. So we basically just evaluate phi at every alpha that's inside of the support of our polynomial. And then this naturally determines a partition where we look at all the indices that have the same value under this map, and that gives us a ji. And excuse me, that should be j0. So basically, given a positive linear map, it will induce a partition of the support of the polynomial based on which elements of the support will have the same value under the image. And again, this seems kind of random. It only makes sense as to why it's here once you see the proof, but for now we have no choice but to accept it. Now, a Rado partition of the polynomial is an order tuple of the support, or an order tuple that represents a partition of the support, such that for any finite coloring of the natural numbers, there exist infinitely many C monochromatic positive linear maps, such that J0 to JL is the partition of the support determined by this positive linear map. And we will see some examples of this because I know this is a lot to abstractly absorb. A Rado set for the polynomial is just any subset J of the support that can occur inside of a Rado partition.
Could you go back a slide, please?
Yes.
Thank you. Okay. Cool.
You have a specific question?
I forgot what capital P was denoting.
Oh, just a polynomial.
Yeah, okay.
Multivariable polynomial.
Okay.
Now, our last definition, before I can try to make sense of this for you with some examples. An upper Rado functional of order m can be 0, that's important, for a polynomial is a tuple where the j's are as before, they make a partition of the support, but now we also have some positive numbers, d0 to dm minus 1, such that for any finite coloring C of the natural numbers and every natural number R, there exist infinitely many C monochromatic positive linear maps such that this JL to J0 is the partition of the support determined by the positive linear map. So this is, so far, all I've said is we have a Rado partition. I've repeated that part of the previous definition. And if we let ML to M0 be the increasing enumeration of the image of the support, then the difference mi minus m little m is equal to di, these positive numbers that we specified at the beginning, whenever I is a indice smaller than m, and then m sub little m minus mi is at least r when I is between m plus 1 and L. So let's actually see some examples of this. I would ask for questions, but I don't think there's anything useful you could ask before you see an example. So firstly, we note that for these two polynomials, the supports are the same. For wx squared minus y minus z and wx squared minus 2y minus 2z, the supports are 1, 2, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. The support does not take information about the coefficients into account. That will be taken into account later, because obviously the coefficients matter, but the support does not realize this information, so they both have the same support. Now, we can take any finite coloring of the natural numbers, and I claim that there exists A and B, such that A plus B minus 1, A plus 2B minus 2 are all monochromatic under this coloring. And I'm just curious, for my statistics, to how many people is this claim obvious? Raise your hand if it's obvious, and I just want to know. Because it was not obvious to me when I first read it, but then I emailed Joel and I was embarrassed because it was obvious later on.
It's not obvious to me.
Okay, well, I guess I'm glad to know that I'm not the only Bergelson minion to whom it's not obvious, at least in the first couple minutes. But basically, I'll just give you a proof because it's short and cute and interesting. You just define a new coloring by the new color of x is the old color of x plus 1. And then you take by Brouwer's theorem, some numbers such that the arithmetic progression and its common difference are monochromatic. And then you see that if you translate that, you get the following. the C color, where you're just adding 1 to everything, is monochromatic. And then you just have if you just do a change of variables, where you let your new A be the old A plus 1, and your new B be the old B plus 1, then you get the desired structure.
Even
So-
after seeing it, I don't think that that's obvious. Like I think it might be obvious if you already have this like shifting recoloring idea in mind, but if you don't, then like.
I mean, sure, that is maybe one way to think about it, because I've never, before this, I've never thought about this idea.
Yeah.
I never had a reason to shift, but I never had a reason to shift additively. I have on many occasions thought about shifting multiplicatively, like the color of times 2 or divided by 2. And then at least that's why personally I was like, wow, I can't believe I thought of all these multiplicative shifts, but I never thought of an additive shift. And even without that, I don't know, this just seems, at least after having read so much Ramsey theory, all these proofs of Hale's duet, polynomial Hale's duet, Rado's theorem, this and that, and then I missed this. I don't know. I was a little sad, but
I think you're good.
now we all know. Now we're more knowledgeable than we were in the past. So regardless, are we all comfortable with this fact now, or should I elaborate on any detail? Okay. So we have this monochromatic structure. So there are infinitely many monochromatic positive linear maps of the following form, where the first coefficient is A, next coefficient is B, and then A plus B minus 1, and A plus 2B minus 2. Right? Certainly, there's infinitely many arithmetic progressions, monochromatic arithmetic progressions satisfying Brouwer's theorem, and each of those corresponds to one of these progressions. So we have infinitely many monochromatic positive linear maps of this form. And now we can see that phi of 1, 2, 0, 0 is going to be A plus 2B. Phi of 0, 0, 0, 1 is going to be A plus 2B minus 2. So then the difference is going to be 2. And similarly, phi of 0, 0, 0, 1 is, again, A plus 2B minus 2. Phi of 0, 0, 1, 0 is A plus B minus 1. So the difference is B minus 1, which we can simply take B to be at least R, because there's infinitely many progressions, or more importantly, we can make the common difference of our progression arbitrarily large. So what this shows us is that the tuple 1, 2, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, comma 2 is an upper Rado functional of order 1 for either of these polynomials. Any questions about this?
And in general, you can just change the coefficients to any integers, I guess, that you want.
What coefficients?
Of P1 and P2.
Sure. For the purposes of determining their upper Rado functionals, the coefficients don't matter.
And so what does the order 1 refer to again? Can you remind me?
The order 1 refers to the fact that we specified one of these common differences.
Okay. And why did you do 1, 2, 0, 0 and 0, 0, 0, 1? Why not 1, 2, 0, 0 and 0, 0, 1, 0?
You could do that, if you just switched the order of these.
Okay. So it's just like
And-
arbitrary, the difference that you take. You're just specifying that
this
exactly
situation,
one
yes.
difference gets you 2. Okay.
In this situation, it's completely symmetric. So it really doesn't matter which difference you take.
Okay.
But if these coefficients were different, then it might matter what difference you take. Not now, because the upper Rado functional will be the same. It's independent of these coefficients. But later on, when we make use of the upper Rado functional, we might have wanted, we might have wanted to have the coefficient of the 4 instead of the coefficient of the 3 showing up here.
Okay,
So theoretically, it could matter at the very end when you're checking for partition regularity of your polynomial as to which one you take. But just for the sole purpose of determining whether it is or is not an upper Rado functional, it does not matter.
Okay, but I guess, yeah, so P1 and P2 don't actually come into play when you are proving that this tuple is an upper Rado functional of order 1.
Correct.
Like you don't actually use P1 or P2. The only thing you care about is the support.
Yes, that is correct.
P, cool.
Any other questions, concerns, comments? Okay. Now the next example is, this other polynomial, the w squared x squared minus y minus z. I will show to you that there are no upper Rado functionals of order 1 or more. Now, just to refresh, the order is allowed to be 0. So, d0 to d negative 1 just means that there are no d's at all. So upper Rado functional of order 0 just means that you can evaluate all of these, I don't know. You could evaluate every element of the support and make them as far apart as you want, which is basically any polynomial, right? If you take any polynomial, then as long as I don't want to say this. Let me not prove it to you abstractly. Let me just focus on the concrete example. I claim that for any polynomial whatsoever, there exists infinitely many upper Rado functionals of order 0, because you could just take any partition and take any numbers whose difference is at least a million, billion, trillion, and once you plug it into your linear maps, the differences are still going to be a million, billion, trillion. It might be annoying to write down the formal proof, but intuitively, it's just what I said. And we're only going to end up caring about it in this one situation for today. So to show that none of the non-trivial upper Rado functionals occur, the upper Rado functionals of order 1 or more, we recall this is the support, or maybe we just note this is the support, 2200, 0010, and 0001 is the support of w squared x squared minus y minus z. And now we take this linear map, just the arbitrary linear map that's monochromatic. So T1, T2, T3, and T4 are just some monochromatic elements of some coloring. And we just observe what are these possible differences, right? For phi 2200, phi 0010, 2200, 0001, and 0010, 0001. Now, technically, there are 6 possible differences. I could consider the opposite order, subtracting in the opposite order. But just to keep it all on one slide, I decided to just allow D to be positive or negative. Because originally D is supposed to be a positive quantity, but then the order of subtraction matters. Now I'm allowing D to just be any non-zero quantity, so that for one of the orders, the difference is going to be a positive number. And my claim is there is no D such that any of these three equations has infinitely many solutions, right? If we want infinitely many C monochromatic, so we want infinitely many C monochromatic maps phi such that these differences are equal to a fixed number D. And then if that happens, we can find an upper Rado functional of order 1 or more. And that corresponds to some D such that this equation, such that any of these three equations has infinitely many monochromatic solutions in any partition of n. Are there any questions so far up to this point? Because I'm about to introduce something new, so I should check here if you're following. So I will prove to you that there is a partition of the integers, a finite coloring, such that each of these equations individually has finitely many solutions. And then that will tell us, that will give us the desired result. Yeah. So I need this other theorem, the non-homogeneous version of Rado's theorem for linear equations. It's somehow simpler to state than the homogeneous version. So the system of linear equations is partition regular over n. And of course, all of the matrix consists of integer entries. If and only if there exists a constant solution. So if there is a trivial solution, right, in any partition of the natural numbers, whatever cell contains x, that's going to correspond to a trivial solution to the system, then the system is trivially partition regular, because this is not surprising, or this is not I don't know, interesting. But what is interesting is the system of equations is partition regular if and only if it is trivially partition regular. If there is no constant solution, then this equation is not partition regular. And I'm going to use this fact up above. So are there any questions about the statement of this non-homogeneous Rado theorem? It does hold, I believe, for any commutative group, but I'll send out a reference for that after the talk just to be safe. It was quite short, actually, the proof for commutative groups. So it's much easier than the proof of the original Rado theorem. Okay, so now we see that this equation is not partition regular, but that's probably not surprising. I think we all could have guessed. If you partition based on the equivalence class modulo d plus 1, then that's a partition that avoids solutions to this. But it also follows as a consequence of this theorem as well. Now, for either of these, we see that we do have a constant solution if D is divisible by 3. So okay, there we go. So we see that 0 is 2. If I move the D to the other side and rewrite the equation like this, where either D is not divisible by 3 and there's just no solution, so we're done, or D is divisible by 3, so this is now a new equation. And in this new equation, if I just give these variables some names, x1, x2, x3, because they're all integers, this equation is not partition regular over the integers by the original Rado theorem, because no subset of coefficients adds up to 0. So this equation only has the trivial solution of 0, 0, 0 for some partition of the natural numbers, which would mean that this equation only has the trivial solution of d over 3, comma d over 3, comma d over 3 for some partition of the natural numbers. And we can repeat the argument here as well. And we conclude that there is a partition of the natural numbers such that each of these equations has finitely many solutions, and therefore there is no upper Rado functional of order 1 or more for this polynomial, w squared, x squared, minus y, minus z. Any questions up to here? And maybe more important than the literal proof that I gave you is just, I don't know, maybe if you can accept and understand the statement that there are no upper Rado functionals. At least build some level of familiarity with upper Rado functionals, since the next slide will contain the statement of the main theorem that uses them. So finally, the theorem that we've been building up to. A polynomial, if we write it as the sum of C alpha x to the alpha, satisfies the maximal Rado condition. Yeah, I guess this is. If for every integer bigger than or equal to 2, there is an upper Rado functional, J0 to JL, D0 to Dm minus 1, for our polynomial P, such that if we set Dm, the next number in the sequence, to be 0, then this polynomial here, constructed from the upper Rado functional, we see that the D's appear here in the exponent of Q, and the J's appear here. If this new single variable polynomial, only of the variable W, has a real root in the interval 1 to Q. And then the theorem, at least half of the main results of this paper, is that the polynomial P is partition regular only if it satisfies the maximal Rado condition. And again, I'll work out an example of this thing. I guess you're free to look at the formula and try to comprehend it, but it probably just looks kind of random until you see the proof and stare at it for 300 hours. But any questions about this statement before I go ahead and apply it to the previous examples that we've been working? Okay. So we already verified a little while ago that 1, 2, 0, 0, comma 0, 0, 0, 1, comma 0, 0, 1, 0, comma 2 is an upper Rado functional of order 1 for either of these polynomials, for either wx squared minus y minus z or wx squared minus 2y minus 2z. So now we pick some arbitrary integer q, and we have, this is d0. So the next d1 has to be 0 by the statement of the maximal Rado condition. Here is the formula just copied from the last page, and sure enough, in this case, m is 1. It is a functional of order 1. So we have the m equals 1 term is q to the d1, so q to the 0 times alpha is in j1, c alpha w to the alpha. And remember, we start with j0, so j1 is the second term. So, I might have gotten this backwards. Yes. Unfortunately, I think I mixed up two of these terms. So this would actually be minus w, and then right, because this term corresponds to the negative z, so that the size of the exponent is just 1, right, z to the 1, and then the c alpha is negative 1, so we get this. And now the next one is going to be q squared, because that's d0. Oops. And now our c alpha is just 1, and our size of alpha is 1 plus 2, which is 3. So we actually end up arriving at this. Now, this is not good because this actually does not have a root inside of 1 to q. It had a root when I had it in the wrong order. Now, I guess the point I'll make now, which I was hoping to make with the next example, is that even though this does not have a root inside of the interval, we have not yet proven, we still don't know whether or not this polynomial satisfies the maximal Rado condition, because we've only constructed this polynomial here for one choice of upper Rado functional. But there could be many other choices of upper Rado functional, and one of the other choices could result in there being a root. In fact, yeah, why don't I do that right now? Well, yeah, sorry about this. I thought I'd check this beforehand, but I guess it still slipped past me. I considered this very issue, but apparently I didn't consider it carefully enough. So the way I'm gonna adjust this, I showed you that this first upper Rado functional does not give us any roots, but now I'm about to construct for you a different upper Rado functional for the same polynomial that does give us roots. So I guess maybe this is interesting anyways, because it shows you some other aspect of this result. Firstly, I change these minuses to pluses, and the proof for that is the same proof, but I just do I color by x minus 1 instead of x plus 1, so I could shift in the opposite direction. And now I see that phi of 0, 0, 0, 1 minus phi of 1, 2, 0, 0 is going to be positive 2. And phi of 1, 2, 0, 0 minus phi of 0, 0, 1, 0 is going to be B. If I change it once again, I guess I have to wait for it to load on your screens. Oh, am I back?
You are back.
Okay. When did I cut out so I could resume at that point?
You said, I'll wait for that to load on your screens.
Okay, yes. I replaced this coefficient with just a again, the same a over here. I'm just repeating it. And now if I do that, I can see that this difference, a plus 2b minus a, is going to be 2b, which is certainly going to be large. So this tells us that Okay, so this is another upper Rado functional. And now, if I go ahead and repeat what we were doing before, so now we're going to have q to the 0 times 1 times w cubed minus q squared w. Excellent. So the m equals 1 term, because this is order 1, the m equals 1 term is d1, which was defined to be 0, times the element in j1, which is here. So that's just going to be 1 times w to the 3. 1 plus 2 is 3. And then I add to that the 0 term. So d0 is 2 q squared. C alpha is going to be coming from j0, which is here. So negative 1 times q squared times just z, because it's w to the 1. And now we see that there is a root inside of the interval 1 to q. Therefore, this polynomial does satisfy the maximal Rado condition, if you choose the correct upper Rado functional, but not for any upper Rado functional. And as I mentioned at the beginning, without proof, it is indeed a partition regular polynomial. But I'm not going to prove that today. Any questions about this first example? Okay. Then I was going to show you one example that this does not satisfy the maximal Rado condition for the particular upper Rado functional that we picked, which I suppose it would now be so for this choice, it certainly does not satisfy, it does not have any roots in the interval 1 to q, for any q that's 2 or bigger. If we do the other choice, then this also does not have any roots in the interval 1 to q, because you're going to get the root plus or minus square root q and 0. And then I'll leave it as an exercise to the reader to check that for any other possible upper Rado functional, you will still fail to have a root in the interval 1 to q, but it should be noted that I have not given you a complete proof because I have not checked every possible upper Rado functional. I've only checked 2 of the possible upper Rado functionals. And I don't know how many there are for this example. I haven't tried to work it out. And sorry, I just realized this is partition regular for reasons I can't mention today. So maybe I should, okay, I guess I'll just show. Well, I won't pick out the correct upper Rado functional because I still want to go over a few other things and we're running short on time. So if you'll excuse my multiple corrections. I probably should have started with this instead, because I was sloppy and accidentally gave you another partition regular polynomial, but I guess new exercise, adjusted exercise to the reader, find the upper Rado functional that will show you that this polynomial satisfies the maximal Rado condition, because we just said it's not either of these first two. Now, since we don't have time to go over the proof, maybe I'll go do that after I mention this genuine non-example. So here we have this other polynomial. P3 is w squared x squared minus y minus z. And I already showed you that the only upper Rado functionals of this polynomial are of order 0. So that's going to make it very easy to check that there is no upper Rado functional for which it satisfies the maximal Rado condition, because there are very few upper Rado functionals of order 0. There's 4 of them. Now, either so there is no D in our upper Rado functional because it's order 0. So our upper Rado functional is literally just a Rado partition in this case. So the partition could either have 3 elements. It could either be some permutation of the support, or it could be 2 elements. So, union 2 of these together, and then the third one is the second element, or theoretically, it could be a single element. All 3 of them together could form a single element of a Rado partition. Now, we can rule out this case because these, if we remember the definition of these J's, these are the elements of the support that have the same evaluation under infinitely many monochromatic maps, phi. And you can certainly partition the integers in such a way that the image of 2, 2, right, 2x plus 2y is not equal to the image of z. This is again a consequence of the original Rado theorem, because no subset of coefficients here add up to 0. So you can find a coloring such that there is no monochromatic map where these elements have the same image, and there's no monochromatic map where these elements have the same image. So this case will never happen. You can never have all 3 of them in the same partition class, in the same cell. Now, obviously, these 2 can be in the same cell, because you could just put the same coefficient in the third and the fourth coefficient in locations, and then the value is going to be the same. So this is certainly possible. We will either have that J0 is here, 2, 2, and then J1 is the union, or J0 is the union and then J1 is the other. So this is a possibility. Regardless, we now see that our sum goes from 0 to 0 because it's a Rado functional of order 0. Q to the D0, which by definition is 0. And we're just adding up over all of the alphas in J0, the very first element in our Rado partition. So if we go through all permutations of having three separate elements in our Rado partition, the possibilities are w to the fourth, negative w, and negative w. None of these have a root inside of 1 to q because the only root is 0. And if we go through this possibility, then that will either give us w to the fourth or negative 2w, which again does not have a root inside of 1 to q. So we've gone through every possible upper Rado functional. None of the resulting polynomials have a root inside of 1 to q for any q bigger than or equal to 2. We only needed one specific q, but it's actually true for every q. So this polynomial is not partition regular. And exercise to the reader, this was independent of the coefficients here. We just need the coefficients to not add up to 0. We use that in this case. Coefficients do not add up to 0. And then really the only special thing about this 2, 2 is that both of them were at least 2. So this equation is not going to be partition regular for the majority of K1, K2, and K3, K4. So any questions about any of these examples? Okay. Any questions about anything else that happened?
So actually, I do have a question. So I know that Nikos with host showed something about squares, that some particular polynomial equation is partition regular, and some other is not, or is not known, something like this. So do we have more general expressions than the P3 that you wrote that has only squares, for example?
I mean, you could do this.
No, I meant in y and z squares to have quadratic terms only. Yeah, something like this. Can we check these cases?
See you, Michael. I
So the question is that the method can be used in general polynomials,
Yes.
general multivariable polynomials, or they have to be, I mean, very specific powers.
Here, I can show this using the method.
Mhm.
So if you do w cubed x squared minus y squared minus z squared, it's not partition regular.
Okay.
I'm 99% certain that it won't be using these considerations.
Okay.
The problem here is that 2 plus 2 is equal to 2 plus 2. So that interferes with the step.
The
It
one with the
interferes
with the
with the step here when I was saying by the original Rado theorem, none of the coefficients add up to 0,
yeah.
and therefore there are no solutions. Now some coefficients will add up to 0. So there might be solutions here. So there will be upper Rado functionals, and then you'll have to check the corresponding polynomials that result from them. And it is hypothetically possible that that this will satisfy the maximal Rado condition.
Okay. Okay. Thank you.
So I mean, you can certainly try to apply this method. You can check the maximal Rado condition for any polynomial. It is certainly a checkable condition. I don't know if that's what you were asking, or if you were hoping for a juicier example.
No. I mean, you answered already. So yes, you can check, but unfortunately, so do we have any other results that you will mention next week, or maybe some characterizations of partition regularity, or the theorem that you stated? It's just one of the directions, but of the characterization.
So one, it's not a characterization at all.
Okay.
This is only a necessary
Yeah.
condition, and it's not, well, I think it's not sufficient, but I'll have to double check my counterexamples on that. But even Joel and company don't conjecture that it's sufficient in their paper. They conjecture that it's sufficient in some very special cases. They conjecture that the maximal Rado condition and the minimal Rado condition combined will be sufficient in some very special cases.
Okay.
Now, maybe I
Okay,
should stop the recording before I start asking about what we're gonna do next time.